aircrafts, number of flight legs, number of maintenance station, number of hub station, number of maintenance station, number of non-maintenance stations. So we have from small network to larger and larger and larger. So, so what we did, we just do a simple comparison. Again, just to keep in mind that the rotation tour model, we try to compare with the flight string model. We acknowledge this is not a fair comparison because the flight string model can do the fleet assignment built in. But in our case, we only do the rotation tour. But again, we can extend it, and I will tell you a little bit. But the whole idea is we want to look at theoretical complexity of how many variables would involve. Imagine if you think about the string, how many sequences of a flight can go. We have millions and millions of possibilities. So we can take this network and we can just generate the comms. Like how many possible sequences one can choose. You talk about millions. It's a huge, even though it doesn't seem so big with only 14 aircrafts, but it's huge. But if one can come up with a smarter way with a greedy heuristic to generate good comms, then you can come up with something better. But if you look at the rotation tour, it turns out that the model is pretty compact. And we run the, we use CFlex, which is commercial optimization tools. Now it was iLog, but now IBM bought it a few years back. So we solved the problem, and within seconds we can solve the problem. And what's neat about this model? Again, with simple idea, I'm not saying the ideas. It doesn't have to be complicated. With simple ideas, the nice thing is because of the network structure. So the linear programming gap, LP gap, and integer programming gap is very small. So you can have a good time solving the problems. Versus if you use a flight string model, you can take a longer time. So again, this is just an example of one problem that I grab on. I want to share with you how we can develop from simple ideas into mathematical programming. So now, again, like I said, this is only one tour, but what about combining with the fleet assignment? So what we can do is we can actually add one dimension of our network. So by adding a set of I, which represent a set of fleet, and we can solve the fleet assignment built in as well with the same network tour. So this is other integrated problem that has been published in the literature, and we compare the result and we show that it's a bit better. Here's some of Dr. Mano's work using integrated fleet assignment with the design. So now, okay, from that, so that was the first part of the dissertation, and then I challenge him because with the daily, it might seem to be a little bit easy, but with the weekly tour, what if you have different schedules every day? So the idea of duplication is no longer easy. How can you solve this weekly schedule problem? And again, although it can be easily incorporated with flight string model, but we said, look, with the network tour, can we do better? Can we incorporate this model? So as it turned out, we can actually do it by doing the network duplication, something similar to what we did before. So we're going to have a bunch of model, and we have Monday schedule, Tuesday, and Wednesday. So all we do is we concatenate by stacker all those network by connected with the rotation arc, the wraparound arc, and we can build the weekly model. Again, the difference from daily schedule to weekly schedule is the complexity grows exponentially. So it's a big, big problem. And so we propose, like I said, I don't want to bore you with the math, but with the simple idea, by extending this network, we can come up with a weekly rotation to a model, which is the first model in the network that we can incorporate the weekly schedule. So what we did was we collect the data from the internet. So we look at different flights. So we have a combined schedule. So we take the fleet of the 757-300s. So we have this number of flight, number of fleet sites, on. And so we challenge ourselves that, look, this problem is still small. So what we did is we combined different fleet into the same network. So we combined Air 330, this one, with 737-800. So we have a bigger test study. And we combine these two to have an even bigger test study. So, and again, the simulation as we combine is about the same as the world's largest fleet, which is by Southwest Airlines with 350 aircraft. So, somewhat we try to see if how can we push it to the limit if we can really incorporate this model and solve real-world problem. Because this is real, this is going to be airline-wide optimization. You're not talking about sub-fleet that you have. You're talking about the entire aircraft that one airline would have. And again, in this case, we use the maintenance day based on FAA, which is 4 days. So what we did was we solved all these problems. And so we can solve even the largest fleet within 422 seconds. So it's pretty quick. And the nice thing, like I said, because the LP and IP solution, okay, the solution of linear programming relaxation versus the integer programming solution is very similar. So we have very close to optimal solution. One is by minimizing penalty cost of short connection, and we separate with the revenue of the through connections. Again, we can solve this problem very efficiently. So again, we're not satisfied. Can we do any better? Because we can still see that for a larger problem, it still takes us 508 seconds versus 1,500 seconds. Can we do better? So we came up with a simple fixing rules, because we know that we have very good linear programming relaxation, meaning that when we have solution that yes or no solution, we have fractional solution. Can we fix certain solutions so that we can sort of tell CPLEX that here's a solution? It's some of the trick that CPLEX likes so much. And as it turns out, we can solve this problem within to the optimal, this one, these two to optimal within 200 seconds. So it's somewhat pretty good. And then we also took it further to incorporate the fleet assignments. Again, the structure of the model, again, the whole idea is not to show you the math, but to show you the structure of the model can be very similar. You can start from one simple thing, and you can do greater things once you have a good model. Something similar to Jay's work, that he starts from the simple micro simulation, and he can expand it into a larger questions. The same thing, that you come up with small ideas, and you have a good model, a good structure of the model, that you can expand it. So in this case, we combine the fleets. So we combine these flights, 757 and 737. So we have a bunch of thousand flights and a bunch of aircrafts. So you can imagine this is one of the largest test data set that's available. So, and we try to solve this problem. And we can solve this problem. Again, when we combine the fleet assignment, we fix the CPLEX with the time limit. So we cannot find any solution, so meaning that it hit the computational time. It takes too much time. We said, look, this is no longer practical, not good for us. So we apply the variable fixing, and we be able to get optimal solution, and we can solve the problem in a reasonable time. So again, so the whole idea is, it's not about speed, but it's about coming up with something good, with a good model to begin with, and you take it from there, and you can expand it and ask different kind of questions, and you can integrate it into other problems. Now, again, as you can see, my comparison is to compare with the flight string model. On the other hand, I'm not saying it's not good. It is good. Actually, I use flight string model for other study as well, but you have to think about, is there any other way to exploit the structure of the problem? So again, I'm talking to you based on from the perspective of the operation researcher, not from the transportation point of view, but we take one transportation problem. So the other problem is called flight conflict resolving problem. So this is a big problem that FAA is dealing with because of the growth of the air traffic, okay, from 2005 to 2024. So you have about 40.8% increase of passenger traffic and 6.2% of the cargo traffic. So it's keep increasing every year. And, but the problem is, in the FAA, and what we call, a part of FAA is called Pacific Organized Track System, of PACOTS. Okay, so PACOTS is in charge of assigning the airspace for the flight here, okay, in this Pacific Ocean here. So what it does is airline would request the track and level and the entry time that's going to get into the system. But of course, there's congestion, just like traffic in Bangkok. So once you have congestion, there's a conflict because there's got to be an FAA separation standard, for example, that, okay, if you fly the same level, fly the same track, you have to maintain, let's say, 30 minutes separation in terms of the flying time. So imagine you drive a car, you stay in the same lane, you stay in the same route, so you have to maintain the separation. Of course, you don't want the other guy's bumper next to your bumper, so there has to be a separation. But in most cases, everyone would try to optimize their own schedule. So the question is, there's going to be conflicts, okay? So let me give you an example. If I did some search on the Expedia, from the flight from LAX to Narita, for example, you can see the flying time here is 12:55. The other is 1:02. Different flight, the same route. Of course, if the airline would optimize based on the optimal schedule, optimal flying pattern, they're going to have the same flight, the same route, and the separation not going to be good enough because you're going to be only 7 minutes apart. So you're going to be nervous to see the other planes on your tail. So there's going to be conflict for sure. The question is how to best organize the conflict. So what happened at FAA is they use what they call track advisory heuristics. So what they do is, okay, first come, first serve. If you come first, you get it, and then you just keep delaying the others. They don't really consider changing the flight, changing the route, or any kind of changing. So they look at one-dimensional. Just keep delaying it. Okay, that's why people in the US not so happy. So again, how can we take this problem as a mathematical programming problem? So one can look at the given track level and entry times. And again, this can be applied to any kind of transportation, can be rail, can be ground and transportation as well. So the goal is we work with FAA and we look at the track change cost, how much is going to change the track, how much is going to change the level. Of course, the fuel burn is going to be different because you're not going to be flying at your optimal level. So we can build this model using flight string model. Basically, we have a sequence of flight for particular track, for particular route, and then we have a sequence of flight, how we're going to assign them. So that's the, because of the time, so I can skip some of this. But one can model this problem using absolute value, what the difference, how much you're going to deviate from what you request, and you're going to be penalized. But then if you want to linearize the problem, you're going to end up with a huge linear program you cannot really solve. So you're going to have a big problem. So you can use a flight sequence model, which is the idea of flight string model. So we come up with a sequence of assignment, and we can cast out the cost of assignment of the string. Because if you assign A, B, and C, so you have this sequence, and you have sequence A and C, and you have sequence B, so you know how much cost you're going to incur and how you're going to penalize it. But would it be better to help you solve the conflicts? And the idea of the string is very simple. So you have to cover the flight once, and you have to assign to the string, and you have to generate a bunch of strings using column generation to solve the problem. So again, to generate all possible string, we talked about millions and millions of strings. So if you have 40 flights being requested, you can have up to 1 million sequence. So imagine how you can come up with a good solution. That's very difficult. So column generation is used to find only good sequence with the low cost. Again, when you generate sequence, you might see, you can eyeball and see that some of the obvious sequence that doesn't make sense. So you can kind of somewhat remove it. And the whole idea of column generation is you come up with a simple solutions, and you calculate what we call a dual cost, tell you that how much you can improve for a particular flight, and you have a subproblem to come up with a better sequence. So you can solve this problem iteratively to come up with a good sequence. So again, this problem is a big problem still because 10 flight candidates on a level and a track, you can have up to 234 million possible sequences. But then we can have theory using the theory on machine scheduling, because when you put in a sequence, you actually put a job in sequence. So we use a simple theory on the machine scheduling. We can reduce from 234 million sequences to only 1,000 sequences. So So basically, we combine different aspects of OR from manufacturing to flight scaling to what have you. You can really try to solve this problem pretty fast. So the idea is of the framework that we develop. So we initialize the sequence, solving the problem, calculate dual cost, try to come up with a better sequence, and we go back until we satisfy to make sure that we've come up with the optimal sequence. So I want to bore you with the math. So we take the simulated data from the FAA simulator. So we look at different flights, we keep increasing. And we look at different horizon because when we talk about the request time for a particular period, from can be 12 to 3 p.m., so you're going to have lesser flights, but you can look at the 24 hours period, but you're going to have more flights, so it's going to be more difficult. So in this case, we just want to show you the TA is what being used by FAA right now. So based on the heuristic by keep delaying, and basic absolute value model is the basic model, and FFM is a flight sequence model. So basically, we just proved that we can help them reduce the delay significantly, help them reduce the average level change and the track change. So, so just prove the point that we can do it, and we can also incorporate equity model. So based on FAA standard, FAA doesn't care what airline is going to get delay, but airlines do. So the question is, if you choose to delay certain flight, and if some airlines happen to be lucky to be, all the flight that got delayed come from one airline, so you're going to run into problem because it becomes discrimination. So we can incorporate the equity consideration into the model. And again, equity model has been well studied by Shalali and his group. So we talked to him and we came up with some idea of how to incorporate the new mathematical model. And as it turned out, after you incorporate the equity consideration, the cost of the delaying, the cost of level change, all the delay increased insignificantly. So meaning that based on FAA perspective, you should consider the equity constraint. Basically, make sure that all the airlines are treated equally. So what other applications of this model? Again, you can think of this mathematical model. Why does this become relevant to you? Because you can think about other problems that you see in everyday life. You can assign workers to different skill levels. Each worker is a track and level, and each task is a flight, so you can think about the sequence, how many ways you can ask someone to do the work for you, or how you assign the assignment to your students. So you can think of vehicle routing problem, vehicle as a track or level, and the site, obviously it can be the flight. Or you can think about the healthcare, for example, assign critical equipment to patients. Equipment can be track and level, and each patient can be a flight. Again, I'm going to spend another 5 minutes just to talk about, again, this is based on research work. What about in industry? What do they do? How do they solve the problem? So what kind of solution they look for? So there's a gap between going from taking real life problem and you come up with the best way to solve it, and going to implement it in practice. So this is a big gap. So just to give you an idea of, just to share with you experience when I worked at ExxonMobil. So the oil supply chain, you can think about going from exploration from the well to production to refining, storage terminal, and ground marine transportation go to the retail markets. So once I got in, I asked them, okay, how did they schedule the vessel scheduling, how to schedule oil import transportation? They use Excel, and they eyeballs it, and they try to match which one would give you the minimum cost. So what we did was, okay, with the oil price, now that it keep increasing and increasing, and I have to pay arm and legs now. So, so one way to do it is to help them distribute the oil better. Okay, so if you think about what you pay at the pump, I'm not sure in Thailand, but at the US, you're talking about the crude oil price is about 58%, and refinery cost, distribution of the market is the transportation and taxes. So again, crude oil we cannot control. Tax issue is not our control. Crude oil you have to ask OPEC because they control the price. Refining, I'm not good in chemistry, so what I can do for them is I can help them distribute the oil better. So what we looked at the how we import the oil from Europe, There's a bunch of major